Hi, this lesson is about the definite integral. This is what we call a definite integral, the integral from a to b of f of x dx. It's defined to be the Riemann sum. Now, what's a Riemann sum? Riemann sum is a sum of length and width of a series of rectangles where the number of rectangles approaches infinity. So that's exactly what we see here. The left side is what we call our definite integral. So let's talk about some of the notation on the left. This integral symbol that represents the integral of a function. The function is called the integrand. The dx is your differential that tells you what you're taking the integral with respect to. And the two, there'll be numbers usually at the bottom and the top of the integrals are called your limits, where the bottom one is called the lower limit and the top one is called the upper limit. The right side, if you recall, that's your summation symbol. This means that you're adding a bunch of terms together, where f of x sub I is the height of the rectangle, and delta x is the width of the rectangle, where, if you recall, delta x is b minus a over n. Now, as the number of rectangles increases, your estimate gets closer and closer to an exact calculation, which is why we're taking the limit as n approaches infinity, because that means that there are so many rectangles within the space that you are not underestimating or overestimating the computation. So basically, the definite integral represents the area under the curve of f of x from a to b. So integrating or integration is the process of calculating the integral. So unlike what we're accustomed to in geometry, your integral can be a positive or a negative answer, and that depends on where f of x is with respect to the x-axis. So the area between f of x and the x-axis from a to b, it would be positive if f of x is above the x-axis, and it would be negative if f of x is below the x-axis. And if you have a combination of both, then the integral will represent the net area from a to b. So, for example, this picture here, number 1. You can see that I have some positive areas to the left and to the right, and then I have this little bit of negative area right here. So clearly there's more positive area than negative area. So the integral from a to b of f of x would definitely give you a positive result. In contrast, example 2 here, I have a little bit of positive area on the left, a larger area below that's negative, and then a little bit more on to the right of that function that's also positive. Clearly, there's more negative area than positive area, so your integral computation would be negative for this second example. All right, so there are some areas that we can compute geometrically, and that depends on the type of curve that it is. So if you end up with a shape that's something that you know a formula for, such as a rectangle, a triangle, a trapezoid, a circle, a semicircle, otherwise it wouldn't be a function, then you can compute those with methods that you've learned in the past. So here's one example. We want to find the exact area under the curve of y equals negative 2x on the interval from negative 2 to 5. Now, negative 2x is a line. When you plot that line at negative 2 and 5, you get this green line that's running from left to right going downward. Here's the points at negative 2 and 5. So at negative 2, it is 4. And at 5, it is negative 10. And then we just connect those 2 points. It goes through the origin. So you can see that when you look at the area of that line with respect to the x-axis, I really get 2 triangles. I get one triangle here, which will definitely be positive because it's above the x-axis, and one triangle Here, triangle 2, that will be negative because it's below the x-axis. So the total area of the curve, negative 2x, from negative 2 to 5, will be the sum of triangle 1 and triangle 2. So remember, the formula for the area of a triangle is 1/2 base times height. So we can easily compute that from the graph. So the first triangle, the positive one, it's 1/2, the base is 2, height is 4. So 1/2 of 2 times 4 gives you a value of positive 4. The second triangle is below the x-axis, so we know that it is negative. So you can go ahead and just put that in right away based on its placement. So that's 1/2 base times height. The base is 5, the height is 10. So here your net area for A2 is negative 25. So your overall area of negative 2x from negative 2 to 5 is the first triangle plus the second triangle. So that's 4 minus 25, which gives you an area of negative 21. Remember, that represents the definite integral. The definite integral has a value of negative 21. Okay, so let's compute this area also by using geometry. We do not need Riemann sums for these because of the shape of the curve. So here, you want to find the area under f of x equal to the absolute value of x plus 2 on the interval from negative 4 to 1. So these absolute value functions have this V shape, and so the corner of the V will be wherever it's equal to 0. And so this will equal 0 at negative 2, which is what you see here. This is the point negative 2 comma 0. And then you also want to evaluate the function at the beginning and at the end of the interval at negative 4 and 1. So when x is negative 4 and you plug it in here, that's negative 4 plus 2, that gives you a value of 2. So that's this point, negative 4, 2. And then you plug in 1 and you get this other point, 1, 3. When you connect these points, you get two triangles, and they're both above the x-axis. So they're both positive. And the total area under the curve of the absolute value of x plus 2 from negative 4 to 1 will be the sum of the two triangles. So as I mentioned before, area of a triangle is 1/2 base times height. So I'm just adding the first triangle and the second triangle. So the first triangle, the one to the left, the base is 2 and the height is 2. So that's why I have 1/2 2 times 2. And the triangle on the right that I call triangle 2, base is 3. And the height is 3, so I have 1 times 3 times 3. So that means I'm adding 4 halves and 9 halves to give me a total area of 13 over 2. Remember that that area represents the definite integral that you see right here. Okay, so let's do another example. This is a different shape. We want to find the area under y equal to the square root of 9 minus z squared on the interval from negative 3 to 3. Okay, so that's actually a semicircle. If you were to square both sides of the original equation, you would get what you see here on the right. And if you move the z squared over, this is the typical equation of a circle with a center at 0, 0 and a radius of 3. So if you know that the center is at 0, 0 and the radius is at 3, and we're only looking at the positive square root, not plus or minus, then you have the circle that you see here on the left. You go a distance of 3 units to the left, right, and above, which is what you see here. So there's your semicircle. Remember that the area of a circle is the formula that you see here. It's pi r squared, but it's not an entire circle, it's half of it. So when you compute it, it's 1/2 pi, and your radius is 3. So it's 1/2 pi 3 squared, which gives you a result of 9/2 pi. And again, in terms of integrals, that means that it's equal to the integral from negative 3 to 3 of the square root of 9 minus z squared dz. But because circles are symmetric, the left side of this circle is the same as the right side of this circle, that you could compute it it represents the first integral, but it also represents the second integral here, which means that it's the integral from 0 to 3, but you double it and you get the same result. You get the same computation. Okay. We can also use the Riemann sum to compute areas under curves, like as I gave the definition before. But first, in order to compute a couple of examples, we need to know something called a power sum. Power sum is basically a formula for a few typical sums. So there's 3 here that I've given you. So the first one says that the sum, as j goes from 1 to n of j, which we know means 1 plus 3 plus 2 plus 3, all the way up to n, you start with the lower index value and you end at the upper index value. Well, you can do that by hand, right? If n is a big number, that could take quite a long time. What this power sum is saying, that you can get the result or the sum value by just plugging it into this formula here. So whatever n is, it would be n squared over 2 plus n over 2. So if n is 100, instead of adding 100 numbers, 1 plus 2 plus 3 plus 4, etc., all the way up to 100, you could simply do plug into the formula and do 100 squared divided by 2 plus 100 over 2 and get the same result. Same is true for the second and third power sum. Second one says that if you have the sum as j goes from 1 to n of j squared, we know that's equal to 1 squared plus 2 squared plus 3 squared, etc., all the way up to n squared. You get the same result in a more efficient way by doing n cubed over 3 plus n squared over 2 plus n over 6. And then finally, I have a power sum for j cubed. So we know that j cubed, as j goes from 1 to n, is 1 cubed plus 2 cubed plus 3 cubed, all the way up to n cubed, and that you get that same summation in this more efficient way by using the formula, n to the 4th over 4 plus n to the 3rd over 2 plus n squared over 4. So we'll be using these formulas in future computations of the definite integral by using the Riemann sum. So here's one that should look familiar. We just did this example by using geometry to compute the area, but we're going to do the same calculation using our Riemann sum definition. So I want to find the area under the curve of y equals negative 2x on the interval from negative 2 to 5 by using the Riemann sum. So in order to use the Riemann sum, you need to compute delta x. Remember, delta x is just b minus a, that's these two numbers on the interval, divided by n. So that works out to be 7 over n. That's basically the width of the rectangles that will be used to compute this area that you see here. We should get the same answer that we got above. Your function value is, remember, the height of each rectangle. So if I'm starting at negative 2, and every width of my rectangle is 7 over n units, then the next one will be negative 2 plus 7 over n. And you keep adding 7 over n until you get to the very last endpoint of 5. So the way you represent that is with what you see here, negative 2 plus 7i over n, where I is the ith rectangle. So if you are on the third rectangle, then it would be 7 times 3 over n, negative 2 plus 7 times 3 over n. Okay, when you plug that into your function, remember your function is negative 2x, and so your x goes right in here. So that's why it's negative 2 times negative 2 plus 7i over n. All right, so now remember what the Riemann sum says. It says that your area is the limit as n approaches infinity. Remember, n is the number of rectangles, so that means there's infinitely many of them, of the sum as I goes from 1 to n of your f of x sub I, which is this, times your delta x, which is this. Now the rest of it is just algebra. We actually did the harder part of the problem, is just identifying what delta x is and your f of x sub I. So in this line, I just distributed -2 across -2 plus 7i over n to give me the limit as n approaches infinity of the sum as I goes from 1 to n of 4 minus 14i times 7 over n. And then in this line, I actually factored out the 7 over n and put it in front of the summation. Notice the summation as I changes is not going to change the 7 over n. There is no I in that expression. So 7 over n will not change or get manipulated until we take this limit, and that's done at the very end. Okay, so in the next line, I'm going to separate this into two separate summations, which is what you see here. I missed the n. So I have the limit as n approaches infinity of 7 over n times the sum as I goes from 1 to n of 4 minus the sum as I goes from 1 to n of 14i over n. Okay, so another algebraic step is right here in this last summation. Again, the 14 and the n are not going to change as your sum changes, only the I is. So I'm going to factor that out as well in front of the summation. So I have 14 over n times the sum of I. All right, so that's when we can go back to our power sum. I used I instead of j, but we can still use it. So notice here I have the sum of I. So we're going to go back to our power sum. This is the sum of j. Sum of j is equal to n squared over 2 plus n over 2. So remember that, n squared over 2 plus n over 2. I'm going to make that replacement right here. So the sum of I gets replaced with n squared over 2 plus n over 2 based on the definition of the power sum. And everything else is just copied down with the exception of this. When you add 4 n times, remember that was one of the properties of summations, that when you add 4 n times, that's equal to 4n. Okay, so now we have to just do a little bit of simplifying and some algebra. So in the next line, I'm distributing the 14 over n across the n squared plus 2 plus n over 2. And that'll give me the limit as n approaches infinity of 7 over n times 4n minus 7n minus 7. There's some like terms inside of those parentheses. So we have the limit as n approaches infinity of 7 over n times negative 3n minus 7. And now I'm ready to distribute the 7 over n across here. So 7 over n times negative 3n is negative 21, and 7 over n times negative 7 is minus 49 over n. Okay, so that's as simplified as possible. So now I'm ready to take the limit. So as n approaches infinity, negative 21 doesn't change at all, but 49 over n approaches 0, so your final answer is just negative 21. And if you recall, that's the same answer we got when we did it with triangles, and that makes sense. You should get the same answer, both the Riemann sum and using geometry when you have special shapes that we know formulas for will give you the same computation. All right, so this next example is a curve, y equals x squared. Y equals x squared is not going to give you the graph of a function with a shape that will allow you to use geometry to compute it. So we're going to find the exact value of this area using the Riemann sum. So you might recall that we used this function y equals x squared on the interval from 0 to 1 in a previous lesson when we were estimating the area under the curve, and we used left-hand endpoints, right-hand endpoints, and midpoints to get an estimate. If you recall, the midpoint gave us the best estimate, but this time we're going to find the exact area using the Riemann sum. So as I mentioned before, first thing you do is compute delta x. Delta x is 1 minus 0 over n, which is 1 over n. That will be the width of a rectangle as you're moving through this space. Your f of x, or your f of x sub I, will be your function value at I over n. Now, why is it I over n? So I illustrated it here. If your width is 1 over n units, then the first rectangle is at 1 over n. The second one will be at 2 over n. The third one will be at 3 over n, etc. I over n. So depending on what I is, you'll be moving through that space until you get to n over n, which is 1. Now, I spread these out so you could see them, but in reality, these would be so tightly compact together that you wouldn't really be able to distinguish where one starts and one ends. So that's just to kind of illustrate what's going on. But you imagine that these are very, very skinny rectangles that where you're not overcounting or undercounting any of the area within that rectangle. So when you're computing your Riemann sum, remember it's the sum of all of the heights times the widths added together. So that's what you see in this line. The height of each rectangle is I over n squared. And why are we squaring it? Because the function is x squared times the width, which is 1 over n. All right, so then we do a little bit of algebra here. So we square the I, so we get I squared, and we square the n, that's n squared. That's what we get here as the summation. And I also factored out my width. And so that went here in front of the summation, again, because as I changes, the n does not change. And then on the next line, I combined the n's. So the n squared in the denominator gets combined with this n. So we get n cubed on this next line. So I have the limit as n approaches infinity of 1 over n cubed times the sum as I goes from 1 to n of I squared. I squared, this summation, is a power sum. And again, that was one of the formulas that I gave you a few minutes ago. So I'm going to replace that power sum with what it's equal to, which is this. So I have the limit as n approaches infinity of 1 over n cubed times n cubed over 3 plus n squared over 2 plus n over 6. Then you can distribute 1 over n cubed across these three terms, and you end up with what you see here, the limit as n approaches infinity of 1/3 plus 1 over 2n plus 1 over 6n squared. And as n approaches infinity, the second and the third term go to 0, and so your answer is just 1/3. And that is an exact computation, not an estimated value. So Riemann sums will work. They're just a little tedious because there's some algebra that you have to get through. All right, so here are some properties of definite integrals that will be helpful for you to know. So first property says that if your limit values are a and b and a is less than b, then the integral from a to b of f of x is equivalent to the negative of the integral from b to a of f of x. So in other words, if you switch your limits, the order of them, that will give you the opposite sign of the area. Okay, the next one says, if a equals b, meaning your limit values are the same, then the integral from a to a of f of x dx is 0. This is a really convenient one for you to remember because sometimes your integral can look somewhat complex to compute, but your answer is really just 0 when your limits are the same. And that's because there is no area under a curve if you're just at a single point, not at a interval of values. Okay, let's do another one. The third one says that if you have an integral from a to b of c dx, where c is a constant, then your area or your integral computation is just c times b minus a. So this one's really easy to explain with a picture. So if you have an x and y axis, and suppose you have a value a here and a value b here, a constant is just a horizontal line. So let's say this is my value c. So this is where c is. So if you look at the area underneath this curve, it's really just the area of a rectangle where the length is c and your width is the difference in your x values, which is b minus a. Length times width, that's exactly what you see here. Okay, then the fourth one says that if you have the definite integral from a to b of f of x plus or minus g of x dx, well, that's the same as taking the integrals independently. So you can treat them as a sum or a difference, or you can take the integrals individually and then add or subtract them, and you get the same result. The fifth one says that if you have a constant that's being multiplied by an integrand, that it's the same as taking the constant out or factoring it out and then integrating from a to b. And then finally, number 6 says that if you have the integral from a to c of f of x dx and the integral from c to b of f of x dx, that's equal to the integral from a to b of f of x dx as long as c is a number between a and b. So you can add areas together or subtract them depending on the problem. All right, so we're going to use some of these properties as well as some information that we've computed before in order to evaluate the following integral. So remember, we just did this one. Given that the integral of x squared from 0 to 1 dx is equal to 1/3, we want to find the integral from 0 to 1 of 4 minus 3x squared dx. Okay, so we'll be using a couple of these definite integral properties in this problem. So first thing I'm going to do is I'm going to use property number 4 right here and split them up into 2 separate integrals. So I have the integral from 0 to 1 of 4 dx minus the integral from 0 to 1 of 3x squared dx. Then in the next line, I'm actually going to be using property number 5 on the second integral because I'm going to factor out the 3 in front of the 3x squared. So I have the integral from 0 to 1 of 4 dx minus 3 times the integral from 0 to 1 of x squared dx. All right, then in the next line, I'm actually going to use property number 3 above because 4 is a constant. So that goes into the next line. So the integral from 0 to 1 of 4 dx, well, that's the same as 4 times the difference in your limits, upper limit minus lower limit. So it's 4 times 1 minus 0. And remember, this integral is equal to 1/3. So I have 3 times 1/3. And when you simplify, you get a final answer of 3. Okay, so here's another example where we can use some of these properties. So if I have the integral from -1 to 5 of f of x dx equal to -3, and -1 to 5 of g of x dx equal to 7, we want to evaluate the integral from -1 to 5 of 4 f of x minus 2 g of x dx. So again, I'll be using a couple of the rules or properties above. Definitely the one for the difference of two functions and the property for coefficients. So that's what you're seeing on this line. I split it up into 2 separate integrals, and I also factored out the 4 in front of the f of x and the g in front of the 2 in front of the g of x. Now I know what these 2 integrals are equal to. That's given in the original problem. So in the next line, I'm just substituting what those values are. So I have 4 times -3 minus 2 times 7, and that gives you -12 minus 14 for a final answer of -26. Okay, so here's another one. There's a part A and a part B here. So if the integral from -2 to 3 of f of x dx is -5, and the integral from 3 to 6 of f of x dx is 18, we want to first find the integral from 3 to -2 of 7 f of x dx. So let's do part A first. All right, so here we have a couple of things going on. I'll be using, again, two of the properties. I have a coefficient in front of 7x, so the first thing I did was factor it out. And also my limit values are in the opposite order. This one says from -2 to 3, but here it's from 3 to -2. And when that occurs, you have to take the opposite sign of the value of the integral. So that's what you see on this line. I have 7 times the opposite sign, which is the negative of -5, and that gives me a final integral value of 35. The next example is asking us to find the integral from -2 to 6 of f of x dx. Notice that the original problem, it went from -2 to 3, and then we start at 3 to 6 for the other part of it. So to calculate the integral from -2 to 6, it's just the sum of these two integrals. Think of it as the sum of two different areas. So from -2 to 3 is -5. From 3 to 6 is 18. So the total area is a value of 13. All right, so let's do another example. So this is, again, using one of the properties. This is when I warned you to try to not to forget it. So we want to integrate the integral from pi to pi of sine squared of x dx. So here's a reminder that when the lower and upper limits are equal, there is no area under the curve. So this integral has a value of just 0. Okay, here's another use of the properties. So we have given that the integral from 0 to 10 of f of x dx is 25, and the integral from 0 to 8 of f of x dx is 11. We want to find the value of the integral from 8 to 10 of f of x dx, and then from 10 to 8 of f of x dx. All right, so this picture here, the curve in green, shows you the integral from 0 to 10. That's shaded in green. It goes all the way across, and that's the one that has a value of 25. But then this other one from 0 to 8, shaded in orange, that one has a value of 11. And we need this piece here that I indicated in blue, the integral from 8 to 10 of f of x dx. So that means I have the big area in green, and I have to subtract out the orange area, which is what you see on this line. The integral from 8 to 10 of f of x dx is going to equal the integral from 0 to 10 of f of x dx minus the integral from 0 to 8 of f of x dx. Since we know both of those integrals, they were given, you just subtract 25 minus 11, and the area from 8 to 10 is equal to 14. The second part of the problem is asking us to compute the integral from 10 to 8. Remember, when you switch your limit, the order of your limits, that just means that you get the opposite sign as your integral value. So since this one was 14, when you switch the limits, that answer is -14. Okay, so that's it for this section. You can try the homework now. Good luck.